All right, welcome to the Explainer. Today, we are taking a seriously fascinating journey from a simple digital command to massive physical action inside one of the most remarkable machines ever built, the Boeing 777. We're going to break down exactly how this incredible piece of aerospace engineering takes a pilot's input and actually translates it into movement through the sky. When you look at the 777 in flight, with its sleek aerodynamic design just cutting through the clouds, it looks almost effortless. But behind that smooth exterior lies an incredibly complex, high-end nervous system that completely revolutionized modern aviation. We're talking about a fly-by-wire system that has to meet astronomically high levels of functional integrity. It literally can't fail.
Okay, let's dive into this. To really wrap our heads around how this aircraft operates, we're going to use a simple biological analogy: brain, muscle, and bone. By looking at the 777 as a living system, we can dissect how tiny digital signals command raw physical power to manipulate the massive structure of the plane.
So here's our flight plan. We'll start with a fly-by-wire brain, explore its triple redundancy, check out the hydraulic muscle and its mechanical execution, detail the flap mechanism, and finally unpack the emergency failsafes. Starting off with Section 1, the fly-by-wire brain. Now, to get how smart this brain is, we kind of have to look back. Older aircraft used heavy physical mechanical cables running the entire length of the fuselage to connect the pilot's yoke to the wings. The 777 scrapped them. Instead, electronic computers convert the pilot's inputs into digital commands. Because these computers react so much faster than a human, Boeing was actually able to make the physical flight control surfaces smaller, which saved a massive amount of weight. And since the system is electronic, engineers baked in this brilliant philosophy called envelope protection. Now, don't confuse this with envelope limiting. Limiting strictly prohibits a pilot from pushing a plane past certain limits. But envelope protection is different. If a pilot tries to, say, roll the plane past a safe bank angle, the computer significantly increases the physical force required to turn the wheel. It acts as a physical prompt, a warning. But if a pilot decides it's absolutely necessary to save the aircraft, they can just push herder and override it. The computer protects, but the pilot stays in ultimate control. And here is a crazy little detail to ensure this digital brain doesn't go rogue. While the 777 is running its highly optimized modern controller, it is simultaneously running a secondary safety controller in the background. And that backup is based on the older, much simpler flight control laws of the Boeing 747. It basically guarantees that even if the advanced system glitches out, the aircraft will always fly safely within the proven old-school aerodynamic envelope of a 747.
Moving right along to Section 2, triple redundancy.
This brings us to the absolute lifeline of the plane, the primary flight computers, or PFCs, hidden down in the electronic equipment bay. Now, what's really interesting about this slide is exactly how they built the redundancy here. There are 3 primary flight computers, and inside each one there are 3 internal computational lanes. But, and this is the genius part, they aren't identical. Lane 1 runs on an AMD 2950 chip, Lane 2 uses a Motorola 6840, and Lane 3? An Intel 8486. They even use totally different software compilers. This is dissimilar redundancy. It means that a single software bug or a specific microchip flaw literally cannot crash all the lanes at the same time. So to actually execute a command, this rigorous monitoring system kicks in. Inside each computer, 2 of those totally different lanes play the role of monitors. They're constantly cross-checking the math, while the 3rd lane is actually in command. Every single calculation gets interrogated from completely different technological perspectives before any digital signal is ever allowed to leave the brain.
All right, on to Section 3, the hydraulic muscle.
Because look, once a digital command is verified, it still has to be executed. And digital signals alone aren't going to move a massive wide-body jet fighting the atmosphere at Mach 0.84. We need serious muscle. To push against that kind of aerodynamic pressure, the 777 relies on an immense 3,000 pounds per square inch of hydraulic pressure. That is 207 bar of localized force, giving the plane the brute strength it needs to drop the landing gear, slam the brakes, and move the wings.
And they don't mess around with failure here either. This muscle is divided into 3 distinct, redundant systems: left, right, and center. The left and right systems get their power primarily from engine-driven pumps, backed up by electric motor-driven pumps made by Eaton. The center system, which is absolutely critical for the primary flight controls, is powered by Eaton on-demand air turbine pumps and electric motor pumps. This separation ensures that even if you lose 1 or 2 whole hydraulic systems, the plane can still flex its muscles.
Which brings us to Section 4, actuation and control. So we've got the digital brain, and we've got the fluid hydraulic muscle. How do these two completely different things actually talk to each other? The answer is the ACE, the actuator control electronics. Think of the ACE as the ultimate translator. When the flight computer decides, hey, the speed brakes need to deploy right now, it fires a digital signal to the ACE. The ACE then shoots specific electrical power to the physical actuators, which essentially opens the valves to let that 3,000 psi hydraulic fluid slam the spoiler surfaces up. The brain directly commands the bone, which drives the muscle.
Let's see this in action in Section 5, the flap mechanism. Let's walk through exactly what happens mechanically when a pilot needs to slow this beast down for landing and moves the trailing edge flaps to position 5. So, the pilot moves the lever, right? The flap slot electronics unit, or FSEU, gets that signal and opens a hydraulic control valve. The center hydraulic system floods fluid into the power drive unit, acting like a motor. This motor spins a gearbox connected to these massive, long torque tubes running all the way through the wings. Now, wings bend and sweep, so these tubes are routed through angle gearboxes until they hit 4 transmission assemblies on each wing. Those transmission assemblies take all that rotational energy from the torque tubes and use it to spin a ball screw. As the screw turns, it physically drives a heavy nut forward. That nut pushes a drive arm, which shifts a carrier beam, and boom! Mechanical push rods extend out to physically deflect the single-slotted outboard and double-slotted inboard flaps down into the rushing air. It's an absolute symphony of mechanical perfection, and the whole shebang happens in seconds. Which begs a pretty terrifying question, doesn't it? If this brilliant system totally relies on electronic brains and engine-driven hydraulic muscle, what happens if the aircraft suffers a catastrophic event mid-flight? What if you lose all the engines and all the primary electrical power? How do you steer a heavy, wide-body metal glider? That takes us to our final stop, Section 6, Emergency Failsafes. To make sure that vital pipeline from command to action stays alive even when everything goes totally dark, Boeing engineers gave the 777 an ultimate backup plan. If power dies, a little door drops open on the belly of the plane, and the RAT deploys, the ram air turbine. It essentially looks like a small propeller. As the plane falls through the sky, the sheer rush of the wind spins this turbine at an absolutely wild 3,920 revolutions per minute. And that spinning prop drives an Eaton variable displacement inline piston pump. That little rat pump pushes 20 gallons of fluid a minute, generating over 3,000 psi of hydraulic pressure that is injected directly into the center system flight controls. It breathes life back into the muscle, making sure the pilot can still physically steer the rudder and elevators. Meanwhile, if the primary flap computers are dead, an alternate switch bypasses them completely, using a secondary electric motor to manually reel those flaps in or out. The plane literally fights to stay alive. Now, why does understanding all this matter to us today? Because this concept of dissimilar redundancy, having totally different systems checking each other, is spreading far beyond aviation. Computer scientists are actually taking this exact 777 architecture and using it to secure multi-million-dollar smart contracts and decentralized finance protocols. By writing the same exact logic in different programming languages, executed by completely different dev teams, they guarantee that a single software exploit can't drain the entire network. So what you should really take away from this explainer is that the anatomy of the 777 is a masterclass in resilient design, and it asks a pretty profound question about the infrastructure of our everyday lives. Think about it. If aerospace engineers are going to these extreme triple redundant lengths to prevent a single point of failure up in the sky, where are the hidden single points of failure in the systems you rely on every single day? Just something to think about. Thanks for joining me on this deep dive.